It's been a full few days since I last saw you up here. So today I'm going to take you through the past week in review. And then at the very end we'll look ahead. Before we do that, I'm going to quickly recap the kind of SLT for alignment pitch that I gave at the first talk. Hopefully now that you've got a little more exposure to SLT, maybe more of it will stick. It'll be a little more familiar. And, well, in any case, a little bit of repetition will do everyone good. Okay, so SLT for alignment. Let's go back to this. The main point I argued is that alignment might require a better understanding of what learned algorithms are in neural networks. Various questions like, why are they using it to learn algorithms? What is the nature of these learned algorithms? How are they represented? How are they implemented? How do they form over the course of the training process? Where do they come from? Argue that data is the most natural explanation for where these algorithms come from. And questions like, what kinds of algorithms do neural networks tend to learn? And related these to questions that are relevant to alignment. So, when do neural networks learn the wrong algorithms as judged by the trainer? How to interpret neural networks, how to steer and align these systems, maybe by developing a better understanding of the developmental process. Not just where algorithms come from, but where goals and values come from, and what kinds of sub-goals might neural networks tend to learn across typical training setups. I developed this analogy of deep learning as alchemy, where you have to specify a culture, an architecture, set a flame, your optimizer, throw in some data, start mixing, and out pop out algorithms. And I argue that, in particular, the way that this works is that data and architecture together control geometry. The geometry together with the optimizer determines the learning process, which in turn gives you the final algorithms in the model. So this is the core idea, right? These four different levels of analysis. We looked at this conjectured S4 correspondence, which posits that maybe structure at these different levels is actually related on a deeper level. You can talk about structure in many different ways in data. You can talk about structure in many different ways in algebraic geometry. You can talk about structure of developmental processes in the way that biologists do, in the way that people studying dynamical systems theory talk about developmental stages, and bifurcations and catastrophes. You can talk about algorithms using the language of computer science. So maybe there are correspondences here, dualities here, so that we can talk about the one by talking about the other. Maybe it goes deeper, maybe the natural way for thinking about algorithms and models is really something more at this geometric level. And we saw this in one particular example that you may have grown exhausted of seeing over the course of the past few days, the local learning coefficient, that simpler patterns lead to more degenerate implementations, typically. And these more degenerate implementations are preferred by the posterior. They're easier to find because they occupy more volume. And that they also generalize better, right? Simpler models generalize better. That's the content of Occam's razor, and it's something that you can formalize with the free energy formula of SLT. Okay, so maybe developing a science of alignment requires taking a step that's analogous to the transition between alchemy and today's modern industrial chemical engineering. So what is that going to look like? In particular, we looked at a few problems within alignment from the lens of this mathematical framework, from the lens of singular learning theory. So interpretability. Right? Maybe by studying changes in the local geometry over the course of training, we can relate those to changes in the algorithm being implemented. This is a basis for developing new techniques for interpretability, for maybe scalably interpreting models. Because when we're dealing with models, at the order of billions of parameters, you need axes of reductions that simplify what's going on. And maybe one very meaningful axis of reduction is looking at relative changes over the course of training. These form a much smaller set of changes than there are parameters. This is relevant for questions like if you have a model that's aligned with you and a model that's deceptively aligned with you, which of the two is the model you want? How do you tell which of the two you actually have? And a related question of when do models first acquire dangerous capabilities? Are these capabilities sticky? Right? Is there some hysteresis involved? A critical period in which the model must learn something or else it never learns something. An analogy with chemistry again, right? If you mix a bunch of reagents together in your cauldron, what kinds of outputs do you expect to get? And can you isolate the chemical reactions taking place in this cauldron to make sure they're taking place in maybe more sterile surroundings, so that you know exactly what you're going to get out the other side? We talked about structural generalization. This approach developed within, or starting to develop within singular learning theory to possibly study out of distribution generalization. It works by relating changes in the data distribution to changes in the local geometry of a particular choice of parameters, to changes in the mode of computation of the model. So this is another basis for potentially detecting things like sharp left turns, and understanding more generally when capabilities break or survive across a distribution shift. So, for example, chemistry. We'd like to know whether our chemical process produces S-thalidomide, which is a useful medication that prevents morning sickness, versus R-thalidomide. They have the same shape up to a mirror symmetry, but R-thalidomide gives you birth defects. Okay, so can we develop an understanding that's as rigorous about the processes taking place in models as that understanding we have of chemistry? And we talked about geometry program synthesis. This idea that you can take algorithms you understand in a setting that is well understood, maybe it's a Turing machine, maybe some other kind of model of computation that's been thoroughly studied, embedding it into a geometric setting, and then studying this geometry and relating it to known algorithmic structure. We can develop this more in-depth understanding of the link between geometry and algorithmic structure. So, what are algorithms even? How universal is this kind of, these different levels of analysis beyond neural networks? Is this something that's true for a larger range of systems, different models of computation? Maybe we can use this to start making progress on questions of instrumental convergence. Given two models with the same loss, you can construct an algorithm that has the same loss, but one of them has a lower learning coefficient. You can say something about inductive biases towards that model with the lower learning coefficient.
What's TM.N?
Turing machine.py, Turing machine.neural network. I created this presentation today between things.
I buy it.
Yeah, you buy it, good.
Did Liam mention in his talk that that project was inspired by the structural generalization point?
Yes, yeah, very much. So we saw this show up in the next slide. Okay, so these three different problems of interpretability, understanding deceptive alignment, structural generalization, and out-of-distribution generalization, and instrumental convergence are all questions we can start to make progress on with these different applications of computer theory. Which brings us to this week. And so let's, as I see it, we have basically three themes of talks that we encountered here this week. Yes, that's because I always see groups of threes.
Could have been four.
Yeah, maybe. So first of all, there's the theme of understanding SLT. Right? There were sessions that are introducing SLT for people who haven't encountered it before, laying the foundations of the field. And here I want to highlight Edmund and give him another round of applause for giving not one, not two, not three, but 4 sessions. And so I asked Edmund to give us an introductory session to the theory of SLT, and that, well, spiraled out of control. That's all I can say. This was followed by a talk by Zach, looking at SLT in practice, in particular local learning coefficient estimation. How do you do this? And some recent results from the past year. This is what we're doing. Oops. Right, so the observation in the series of papers involving Edmund, Zach, George, Susan Wang, who's not here, and Daniel Murfitt. Learning coefficient can be scalably and accurately estimated in some settings where we know the ground truth. In toy settings, such as deep linear networks, and particularly the toy model superposition, we can really make predictions using SLT that bear out empirically. You get a little transition. I never grew tired of this one. Right, and so you see this eye candy showing you relations between structure as you would intuitively understand it and this local learning coefficient. We also saw the example of models trained on more realistic data, so the developmental landscape paper where we looked at the linear regression transformers that showed up again in Liam's talk, and small language models where we found this hidden stage-wise development that could be revealed by looking at changes in local geometry over the course of training time. So maybe this developmental approach to interpretability really is viable. Okay, so that's, well actually, we're already getting into the second theme, which is validating SLT. So we see that in a range of techniques. So Lucius and Jake presented work that they've done related to SLT and trying to use it for interpretability. We saw work by George presented. So the current state of the art of SGLD calibration we just got out of the session. And George earlier this week presented ongoing work on these refined local learning coefficients. So can we extract more information using this technique of learning coefficient estimation? So we have some of these pretty pictures where we see that these refined LLCs pick out different kinds of attention heads, shows us patterns of differentiation over the course of training, and also reveal patterns of specialization where certain heads favor code over other kinds of data. And we saw a few very concrete applications, especially in models trained on algorithmic tasks. So Einar presented on his sorting algorithms with almost hundreds of these beautiful jets, where you see decreases in local learning coefficient associated with the model specializing its heads to different kinds of patterns. Still not fully understood. And then this morning, Liam presented on essential dynamics, retreat from ridge, and this explanation revealed by SLT. And maybe the last theme for this past week was the idea of extending the theory, extending the foundations of SLT, setting ourselves up for the next stages of application. So we saw that in work by Miki Oyagi and Simon in the context of these deep linear networks, and understanding what the learning coefficient is here, different ways of theoretically deriving these learning coefficients. We saw it especially in Simon's talk on jet skis, which is the forefront of theoretical SLT. So I'm excited for the next conference. Who knows where we'll be next. And then this morning we had a presentation. I missed the quote.
It's a Chrome Roads, apparently.
And then you gave a great talk this morning on Newton diagrams, another potential approach for computing learning coefficient. Okay, so that's the past week. What now? Right, what's the next steps? I'm going to start by highlighting some of the research that we, Timaeus, dance group at the University of Melbourne, our partners at the Gradient Institute, are working on. And then, well, once we get to the end of that, maybe we can actually open up to discussion and talk a little bit more about this informally, where people are interested in what kinds of things they would like to see. Okay, so what's next? Well, on the capabilities front, right, it's clear. Progress is fast and continuing. Compute's still going up, loss is still going down. And we can debate exactly what angles these are and how long it'll be conceivable for compute to keep scaling the way it's going. But this seems pretty damn sure to me. What's less sure is how does this translate to specific capabilities in computers? right? That's the whole difficulty of the scaling laws is we can predict loss, but we can't predict performance on particular downstream tasks. So that's this whole world that's unexpected and unknown to us. We can make a few predictions about where SLT is going over the next year or so. Next year and beyond. So first, evaluations. So if the past year was focused really on trying to validate that SLT is a theory, says sensible things about neural networks, well, for Timaeus, the next year is really focusing on making immediate real-term impact for ASMT. So what can we do with the local learning coefficient as it is today? Maybe refined local learning coefficients are allowed in this question as well. We think it has something interesting to say about the question of how reversible is safety fine-tuning. There's this observation that safety fine-tuning is very easy to break usually. So a variety of papers have shown that you can fine-tune models on maybe tens of examples for pennies and get it to produce harmful outputs. So can we say something about how easy it is to reverse this safety fine-tuning using the local learning coefficient? We expect this to be the case because of its information interpretations, but we think there's a lot to do there. Another related question is, how robust are current models to jailbreaking, many-shot jailbreaking? We think that the learning coefficient also has something to say about this sensitivity of models to adversarial attacks. And in fact, these two questions might actually be deeply related to each other. So robustness of safety fine-tuning of alignment techniques in general might be something that we can start to probe with the local learning coefficient. Maybe last, looking in settings like sleeper agents, places where we've put a Trojan or backdoor into a model. Can we detect which of two models has a backdoor? Seems pretty likely that we'll be able to do something like this in the near future. Okay, so what can we do with the local learning coefficient today? We can start building a more rigorous science of understanding the robustness of current alignment techniques and pointing out their failures.
Maybe just to give a very brief plausibility argument for that. So if you think of the LLC as computing something like the complexity of the model when it computes on certain data, namely the true distribution, if that's what you're doing. With the refined LLCs, if you estimate the LLC on other data distributions, there's like some theoretical reasons to think you could think of that as the complexity of the model when computing on that specific data. Now suppose you take your data distribution and you have a certain word that's either in it or not. And if the word is in it, it does one thing, and if it's not, it does another thing. Well, those two pathways might have different complexities. And so it makes sense that if you could detect the variation in the model complexity as a function of the data, that you might make some progress on this kind of question. So that's roughly what the argument is.
So, applications for evaluations. Another main axis of the work we're doing is very much engineering focused. It's about scaling local learning coefficient estimation to state-of-the-art models. So billions of parameters, tens of billions of parameters and beyond. Although in practice we expect that showing that it works at 1 billion or 10 billion parameters is enough. We can hand it over to the labs at that point. So George spoke about this right before this, but the question of how to choose hyperparameters is one that we're still developing. So we're working on a project in terms of understanding how to choose parameters. This is difficult, and it's something that makes going to larger models extremely difficult because often there are grid sweeps involved. So if you have to do that for very large models, the compute grows very quickly. The questions of how local learning coefficient estimation relates to quantization, LoRa and other parameter efficient fine-tuning techniques, weight refinements. Maybe there are easy wins we can gain from using these kinds of techniques, and that also shows up in the work we're doing on fine-tuning that I described in the evaluations applications. And it's not just the question of can we scale to larger models, but can we actually scale larger models and then learn something new about these models? So applying with the aim of learning new things about GPT-2 small and beyond. And then let's talk about extensions to the foundations to the theory. I've been focusing very much on, in this talk, on applications. So the way I see it from my experimental corner, where I try to go out and actually use this stuff in the real world, is the role of theory is primarily to give me new tools, sensible tools that measure the thing I want to measure, and then extract as many bits as possible from the data I have. Okay, so one thing we're working on is using SAEs, for example, to try to develop data sets that elicit specific capabilities. So using this in combination with the data refined local learning coefficient can give you much more refined learning coefficients to measure. Complexities of particular capabilities, particular features in the model. What can we measure with jet schemes? I think we're not quite there yet, but maybe closer than we like to think. Maybe next time we have something. Simon can comment on that. And there's of course other constants in the theory that we can start to measure. So the singular fluctuation, gotta know what the picture is. But the singular fluctuation is a thing we can measure. It's a little more difficult and finicky than the local learning coefficient, but we expect to be able to do this. It's also related to sort of data curvature tensor that seems like a rich object that we want to study and we want to understand better. So there are more fine-grained tunes just across the horizon that we are going to start with. So maybe 3 axes of development are go as big as you can, extract as much information as you can, so scaling and extending the theory and tools, and then applying it to immediate real-world safety problems, such as understanding fine-tuning, jailbreaking, and these other immediate problems. We think we're on the critical path to making a difference for evaluations, for interpretability techniques very soon, and eventually alignment techniques, developing better ways to align models. So progress is fast. Now let's speed run all of thermodynamics, chemistry, and statistical physics. Thank you. Yeah, we have quite a lot of time still, so we can take some questions and maybe turn this into a discussion.
How about theoretical directions that you're interested in? Maybe
Genuine too.
Theoretical approaches that we're interested in. Not sure what the question.
For example, like, you know, maybe a better theoretical explanation of what lambda hat is when you're on the basin.
Yeah. I guess there's many such questions. It's sort of hard to enumerate them.
I mean, that one might be an important one, but are there any others?
Yeah, that I guess we're sort of actively thinking about. That's definitely an open question. Yeah, I think this is too open-ended. I'm not just going to reel off a list of open problems, but in terms of priority areas, obviously we think something's a priority, we're tackling it ourselves. There's still plenty of scope for investigating toy systems and small systems, right? Actually, that's one thing I want to emphasize. I mean, it's appropriate, of course, for Timaeus to go out and be trying to go bigger because, you know, there isn't time to just focus on small systems forever. But going with bigger systems involves all sorts of nightmares, right? Hyperparameter selection just being one. Like, it's really not easy and not the kind of thing you want to do. You want to push on fundamental understanding necessarily. So I think I'm very enthusiastic about like the work that Einar did with the algorithmic transformers and like just doing more of that kind of thing. So, for example, like what's going on when the LLC increases exactly? Like we know more information is going into the model in some tautological sense. That's what the LLC is measuring. But like, what does that mean? Are there facts? Is that where is it memorizing them? Can you see that with the LLC? What happens when the LLC goes down? You know, in some examples, it means something like the algorithm getting cleaned up, but you know, that's some kind of very primitive explanation. So what's actually happening there? Like very systematic study of these things in small systems where you can really tell what's going on is still quite open. I'd be very excited to see work in that direction.
And including many classes of machine learning systems beyond when you want to.
Yeah.
Yeah.
And and for this there is a lot of prior theoretical work by Watanabe and students around like more classical model in Bayesian statistics and computation of their line predictions.
And Bayesian networks would be a great one, something to do. So there's some theoretical results by Wernick and others on learning coefficients for Bayesian networks. Bayesian networks have a kind of rich data structure. To study the correspondence between that and to just empirically attack that or theoretically.
G-phonets, of course.
And Markov model.
Yeah.
G-phonets.
Sorry?
And G-phonets.
Yeah, sure.
Yeah, I'll highlight that on devinterp.com/projects. If you're interested in working on something like this, we have a list of project ideas. There's some systems described that you might want to investigate.
We have, I just wanted to say, so we have a Discord server and a papers channel. And I used to joke that basically every paper I would say, what can you do?
That's a good one.
So basically every machine learning paper, so yeah.
And
Now,
for
when you have your
context,
SLT gap on, so right for
and for reference, Simon's posting 5 papers a day. So that's a lot.
Yeah, the problem is convincing the referees that that's the right thing to do.
This may not be a good one. In terms of measuring LLCs, well, you guys are doing it empirically by the models of training. I'm curious if anybody is thinking about theory that they will help have a generalization of the LLC that's sort of defined everywhere on the lost landscape, or in some sense goes beyond exact local minimum, but you know, some sort of rigorous footing for that, or quasi-rigorous.
Yeah.
I mean, there is a global learning coefficient. It's well defined. It's just hard to measure.
That's global, but I need something. Well, there's 2 different things. One is just having it defined at a bunch of different places. So not global, still local, but not just at the minimum.
So there are quantities that you can define, like for instance, like a behavioral LLC or something that's defined everywhere. Things like that. It's related but different.
Right. So then the question is like sketching out its properties.
Yeah.
Yeah, I mean, so one is you can think of this behavioral LLC, which only depends on the model and not the data as kind of a singular analog of the Fisher information.
Yeah.
Also, it's
Yeah.
bound just of the model and tensor.
Yeah. You can relate it to various like fractal dimension.
What's your favorite paper on that?
Oh. I don't think that's a paper. I think that's like your talk to me or something.
A very closely related thing would just be a notion that's, I mean, this is a physicsy buzzword, but like a effective theory in the sense that it's, you know, some sort of local quantity that is defined, even if you're coarse graining locally or adding noise locally or something like this.
Yeah. No, I mean, I think something like very central to, I think, how I think about SLT is like imagining different sort of degeneracies as different effective models in the neighborhood of that degeneracy and sort of describing what exactly that effective model is. I think is like, I would be very interested in that. And I think there's a few like approaches we're thinking about that maybe might lead towards there, like jet schemes or correlation functions or things like that.
Yeah, I was curious. I guess most of the examples that you show are
and some convolutional networks. And also in QD, quantifying the degeneracy, the new version of the paper, right?
In the original version there was an M, isn't there?
Yeah.
There's a misread one, but I think we were talking about ResNet.
In the newest version.
But what you see there is the learning coefficient curve is much more boring than the transformers we see here.
Yeah.
So it does seem to learn something steadily.
Mm-hmm.
Maybe we can break that apart with a refined of the learning coefficients. That's
Yeah.
something that I'd be very excited to see somebody actually
Yeah.
investigate further.
It's also a very interesting direction that at the present moment we're not planning to explore, which is so Chris Oller has asked me about like the relationship between the development of features over training and the development of like the model from our point of view. And those two things are likely to be related, of course, because if the story about features is true and the story about internal structure computing features is true, then like as the structure that produces the feature develops,